Welcome to PRK Study Circle. Today we are going to compare analytical method and numerical method by taking the example of plane failure. Here usually we compare an analytical method and numerical method factor of safety. Then we can say that which one is the uh, good and which one is the correct, and simply it's a validation of numerical method. So let moving on to the second slide. Here you can see study object nothing but here analytical method is nothing but simply mathematical calculations, just using the putting the formulas and getting the answer. That's the analytical method. Generally we have mathematical formula, then we will apply those formulas to calculate the factor of safety. In numerical method, here you can see numerical method. I will use the Roxanne software. In the Roxanne software there is a Slide2 software is there. In Slide2 software which work under using the formulas of find element method, that is a numerical method here I will use, and after that I will compare the results of analytical method and a numerical method. Then the task will be completed. Then here you can see the some fundamental concepts like the plane failure. What is the plane failure? Here you can see the sliding of rock along a discontinuity plane that dips out of the circle. Just we can consider only here one discontinuity plane which slides from the slope. Simply we can hear the plane failure, and some conditions are there here. So the dip angle is less than slope face angle, and dip angle is more than friction angle, and this lateral release surface are present. Here you can see the dip direction. Here these conditions are very much useful for analyzing of kinematic analysis. Nothing but in stereo nets, these are very much beneficial to analyze in 3D view into two-dimensional. That is important for kinematic analysis. Here we are using, here saying that here analytical method and numerical method comparison. It's moving on to third slide. Here you can see the parameters. Nothing but we have to give the inputs for analytical or whatever maybe it's a numerical method. Generally the unit weight is 25 km cube, and the friction angle 29 degree, and discontinuity dip angle alpha 35 degree, and cohesion 350 kilopascal, slope height 100 meters, and slope angle beta 45 degrees. These are the input parameters and this is the formula used to determine the factor of safety in analytical method. And these are the key assumptions. Nothing but the rigid planar block sliding on a single discontinuity surface, only single discontinuity, and limiting equilibrium approach. Nothing but forces balance at a point of failure, and Mohr-Coulomb criterion we are using for strength envelope. And here we are, there is no water pressure or seismic loading dynamic analysis, no dynamic analysis, and any no pressure, water pressure. Simply these are the key assumptions here. These are the method of calculation. Nothing but first we initially calculated the failure plane length, nothing but the area. Here we calculated area 174.34 meter square. Here meter is came. Actually this is a meter square, and this is a weight of the block, and resisting force, and factor of safety nothing but resisting force by driving force. We calculated the resisting force here and driving force here by dividing those things from resisting force by driving force. Finally we got the answer 2.78. In analytical method the factor of safety is 2.78. If the factor of safety is 1 in ideal method, in ideal we can say that the factor of safety is 1, nothing but it is a stable. But in practical condition we usually consider from 1.3 to 1.5, but the factor of safety is 2.78 here. So there is no slow failure. But wow, ultimate agenda is not finding the factor of safety. We are going to compare the numerical method and analytical method. So here the factor of safety is more than 1.5, slope is stable. Okay, then this is final output we got from analytical method, and now we are going to analyze the factor of safety in numerical method in Slide2 software. So here there are different methods of to find out the factor of safety. I am going to find only the three methods here using Bishop Simplified and Janbu Simplified and Spencer method. But whenever you calculating or finding modeling in the Slide2 software, you can see n number of methods. I will show those things. They're very much very interesting. You can see the Slide2 software. The person, you can also do those calculation if the person who has the license of Slide2. Here this is a 2D analysis. Now I will show the method of approach to calculate the factor of safety in Slide2 software. For that I have done already. I have done model, but I will show step by step here. Now so for that, from fundamentals, the person who don't know the process, then I will, if this video will explain the step by step from initial to final. Then you have to choose. These are the different methods: Bishop method, jump method. I am only choosing 3 methods: Bishop method, jump method, and Spencer method. Then you have to select the groundwater. We are not analyzing any groundwater. And okay, click on OK. Then we'll finish. Now go to analysis section. Then give us a title, the project title. Here I am also explaining the numerical analysis simplified. Just name it as a factor of safety. Then we have to plot a geometry. For that you have to choose boundaries, then select table, then you have to enter the coordinates here. Same method what we have done in the analytical method, I am taking those coordinates only. That geometry, we have to create geometry here. That's why we have to make coordinates. I am assuming the boundary as 200 meters. 200 meters. That's why these are the coordinates. You will have to enter those coordinates. This 100. After entering this all coordinates, you will get one geometry, that is slope. You will get that one. Then just click on done. This is the final geometry of the slope. So we have to add weak layer, nothing but the discontinuity plane. Go for the boundaries and select add weak layer, then select the edge of the toe, and then here we have to give the coordinate where we have to add that one weak layer. So then you can go enter coordinate table, that is 148.815 4. Okay, that is 100, because the 100 meters is the height. Here you will get we have to add the weak layer, that is the weak layer, nothing but the discontinuity plane. Now we have to surface options, nothing but surface, it is circular or planar or non-circular. So we are using user defined, nothing but we have to add planar. Non-circular, irregular, not irregular, it is a planar. That's why I am choosing user defined. Then add surface, then I am adding surface, that. So I have done that. Next we have to add material properties. For that we have to go for the properties, then material define materials, click on materials. Here you can see you can have to enter the unit weight, cohesion, angle of internal friction, and the failure criteria is Mohr-Coulomb. So the unit weight is 25 kN per meter cube, and cohesion is 350 kilopascal, and angle of internal friction is 29 degrees. After entering these values, then click on OK. Now we are going to compute and interpret. Compute nothing but calculation, interpret nothing but results. We will get the results. First of all, we have to compute nothing but the software will calculate the entire geometry and the discontinuities, everything. It will take some time, and then we have to interpret then we will get the results. We got 2.877 Bishop Simplified 2.88, and there are 2.88 and another method also there. This is a factor of safety, shown the factor of safety here. Now now you can see the another method. It will show query, add query, nothing but here we can see the factor of safety again, 2.877. Now graph, then you can see create graph, nothing but the discontinued plane graph, distance versus base normal stress, and yes. Now you can see the different factor of safeties. Janbu Simplified 2.78 and 2.779, I think, but 2.78, and in Spencer also same 2.780. So because we have taken only 3 methods for calculation, we got the 3 factor of safeties. So let's compare the analytical method and numerical method. You can see the slices of discontinuity. We have there are each and every slice is there. Now you can see the each and every slice factor of safety. For that you can go for you have to select the slice, and you have to click on the slice that gives the information regarding that slide. Let's see the slide 16. You can see the factor of safety of 2.7795, and each and everything is there: slice weight, base length, base shear force, and each and every property of the slice. This is about the numerical method analysis. Finally, we got the output of different methods. 3 methods are there, approximately near to the same analytical method and the numerical method. Let's coming on to our presentation here. This is about that one. This is a numerical analysis we already. So from you have seen analytical calculation, the factor of safety, and numerical calculation factor of safety. Here just in analytical method you use the factor of safety is 2.78. In numerical method, in 3 methods are there: Bishop simplified method 2.88, and Janbu simplified method 2.78, and Spencer 2.78. So nearly equal to the same analytical method and that numerical method. So that is a comparison. The 3.6% is difference there. This is we can say that is an excellent agreement. The validation is okay. Usually the validation up to 5 to 10% is okay, but we got 3.6% because it is a simple method. That's why we got very much less difference. But if you take the in number of discontinuous planes, there will be a different. But in analytical method is very much difficult to calculate that multiple discontinuities. But in numerical method is very much simple. That's why we are going to the numerical method. This is analytical simplification. That same thing. It is a very much difficult. In numerical it is very much easy. And in three methods there is a very much 3.6% is the difference is there. So up to 10% we can consider the we can negotiate the up to 10%, no problem with that. If more than 10%, there is compared with an analytical and numerical, if more than 10% is there, just we have to negotiate and we have to do again. Validation is not correct, so we have to do it again. That's why we are saying that here. So we have compared the analytical method and numerical method, and you can see the very much difference is very much less. And these are the material properties, and you can see analytical method and numerical method. We are using Slide2 software. After conclusion, we can say that the difference is very much less, that is 3.6%. So whenever you are going to do research, in that you have to validate with the analytical method or empirical method or instrumentation values. Already there existed the values. That's why because whether the numerical method is right or wrong, how can you say that? So for that we need a standardized validation. That we can say that in instrumentation and instruments we use to calibration the instrument. Without calibration we can't go to take the readings. Like that we have to validate the numerical method with the analytical method or empirical method, or instrumental values and already existed values. Then we have to do research, or we have to do any model that. So up to then we can say that it is a correct one nearly. But whenever you are validating, that error should be within the 5 to 10% range. So this is the ultimate agenda of this. We have compared the analytical method and numerical method. We found the factor of safety in analytical and numerical, that is very much, the difference is very much less. So we can validate this. Slide2 software helped me as to find out the factor of safety of the plane failure. Okay, now you learn the validation of a numerical method, and you have learned the Slide2 software how to do a model, a simple model, not the complex model. And you have learned the analytical method, numerical method, and comparison and validation. Okay, I think thank you for listening. Bye, see you in the next class.